Okay, so let's do a few more examples. Now remember, stoichiometry is the relationship between the reactants and products analytically, mathy wise. And don't forget, we have the 4 steps on all stoichiometry problems and analytical problems in here. That is okay, so balance any equation. If there's no chemical reaction involved, you can skip this step. Okay. So the only thing I added this time today is number 2. I said sometimes there are 2 givens. What do you do then? Okay, we haven't come across that yet. Normally there's 1 given, normally. Now your next chemistry class may or may not, depending on which one you take, may or may not include the limiting, the 2 givens, which have a limiting reactant. If you take 1A or 3A, you will have that for sure, guaranteed. I'm not sure about 2A though. 2A you may not. I know in Sac City's 2A equivalent, they don't, which should be on par with this class here, the 2A class here. All right, so let's do another practice problem here. And we are going to have, let's have a different. Okay, so we've got methane burning and oxygen gas. Okay, so how many grams of water produced if 5.67 grams carbon dioxide are produced? Okay, so step one is balance the equation. Is this balanced the way it is? No. So I'm going to balance it really fast, but you need to know how to balance equations. So we have two of those, two of those. Okay, it's balanced now. Now we're going to continually use this equation today for however long it takes for this lecture. So we're always going to be using methane, oxygen gas, totally combusting to water and carbon dioxide. So each time we do a new problem, we're going to be using this equation, okay? So I'm not going to keep repeating the same equation. Okay, so there's only one thing given here. Yeah. On the right, there were until I balanced it.
What?
Now that I balanced it, there are four on the right, four on the left.
So yeah, it will be two.
You see where the 2 and 2 come in? Okay. Yeah, because we have 2 here, 2 there. Okay, so if in doubt, convert to moles. So first step always in stoichiometry is whatever you're starting with, no exceptions, convert to moles. Boom. So we're starting with grams of water, carbon dioxide. I'm going to end with water. Okay, so we've got to convert this grams of water, or grams of carbon dioxide to moles of carbon dioxide. So it's going to be 1802, 1 mole. Where did the 1802 come from? Periodic table, right? 2 hydrogens, they're 101 apiece. Oxygen 16, so that's 18.02. Someone spilled something sticky up here. And they didn't have the glass to clean it up. Okay, so now we have moles of carbon dioxide. Now we need to go to the balanced equation to get the ratio of water and carbon dioxide. That's the next step in the middle. So this is given to moles. This step here is from the periodic table. Yeah.
If that's water, why does it can't say on?
Oh, because I goofed up. When I ask that, everyone says, "Oh, in the periodic table." You got to use the right elements though in the periodic table. Okay, so carbon.
Yeah, that's what I was thinking.
Okay, so carbon's 1201 periodic table. Oxygen is 16 apiece, so 2 of them is 32. So that's 4401. And once again, I'm proving I'm human. Well, thank you for asking that though. Okay, now we have moles of water. We don't want moles of water, we want grams of water. So now we need to take the moles to what you're trying to calculate. All right, so that means we need grams on the top, moles on the bottom, so the moles cancel. And that's the 1802. Yeah, so now we need to get this ratio from up here. So it's going to be 2 to 1. Okay, so the moles cancel, leaves us with grams of water. That's what we're trying to calculate. And this is worth 90% of the points. So this is a 10-point problem. You get 9 points without picking up your calculator. Okay, are there any questions about this guy? I'm going to do a couple more simple ones like this, but I want to make sure. Now, this is very consistent with that homework I gave you. Remember, I substituted the worksheet for the next dry lab coming up. And the name of the worksheet is called Dry Lab Stoi, short for stoichiometry. Okay, so let's do another one here. Okay, now remember there are 3 conversion factors you need to know. 2 of them are universal, and the third one you have to look in the periodic table. So first one is gases, 22.4 liters per mole. Boom. Doesn't matter what the gas is, it's always at 22.4. Avogadro's number, 602 times 10 to the 23rd. Regardless, it's just like a dozen. Doesn't matter how many you're counting, including the geese outside. We saw a mother goose who had, what are they called? Gouslings? What are baby geese called? I don't know. Yeah, whatever. Baby geese. They were like, what, 5 of them or something like that? Yeah, they were like about like this. Like baby anything, they're cute, what can I say? All right. And then the last conversion factor, see how easily I get distracted? The last conversion factor is going to be coming from the compound itself. That you need to get from the periodic table. Now, remember on the periodic table, those decimal numbers represent grams of that element, 1 mole of it, 602 times 10 to the 23rd. So if we went to carbon and took 6.02 times 10 to the 23rd carbon atoms, they would weigh 12.01 grams, molar mass. Okay, understand that. Sometimes in your next class, they're probably going to call them AMUs at first. And then eventually when you get a stoichiometry, then it's going to be molar mass or grams per mole. AMU stands for atomic mass units. Same numbers though, just different label. Okay. Okay, so I changed it to working with gaseous carbon dioxide now, which is more realistic because this reaction would produce, as you know, burning methane, which is the natural gas out of the wall, produces a lot of heat. So it's probably going to be in a gaseous form. All right, so same equation, same balanced equation up here. So now we're starting with liters, gaseous liters. So to convert liters, gaseous liters to moles at STP, it's going to be 22.4. And the ratio is going to be the same, water to carbon dioxide. And then we need grams of water. So that's going to be the 1802. So everything cancels. I'm left with grams of water. Okay, is everyone comfortable with this? Because the given is gas, we have to use the 22.4 liters of gas per mole. That gets us to moles carbon dioxide ratio from the balanced equation. And then we convert to grams to get it over to grams of water. Okay. All right. I'd like to throw in two givens now. Okay, two givens complicates this dramatically. You'll see in a minute how dramatic it is. How many grams would it produce? Okay, so we got methane and oxygen, and we use some of each. So how many grams of water produced? We have two givens. Two givens. So as an aside, okay, so if I have 5 frames and 6 wheels, how many bicycles can I make? Well, if we had 5 frames, how many wheels do we need? 10, 2 each. If I have 6 wheels, how many bicycles can I make? 3. So which is more, 3 or 5? One frame per bike. So if we ignored the wheels, we can make 5 bicycles, right? If we ignored the wheels, we can make 3 bicycles. Now, so we have 2 givens. Given 1, given 2. So you've got to do in your mind a calculation. First, ignoring this. First with the frames, 5. Next with the wheels, ignoring the other. 5 and 3. 3 wins.
Because it's full. Would it be a full bicycle then? Or is it just?
We just don't have enough wheels to go on with the number of frames. So we can't make more than 3 bicycles because we don't have enough wheels. So the number of wheels limits the number of bicycles we can make. Now this works in life. And I can go on philosophically about some things, but basically in chemical reactions, it's the same thing when you have 2 reactants. One of them is not going to be enough for the other one. So we have to do a calculation as if they were in isolation and then see which one is less. And that's the one that's going to limit the reaction. So in this case, wheels limit the reaction. Okay, does this make sense? Okay, because this is exactly what we're going to do with chemistry now. Exactly the same. Okay, so we've got 2 givens. One is methane and one is oxygen gas. One of them is going to limit the amount of water we make. So we have to do 2 calculations now to figure out which one is less. And that's the one that limits. So when you think of limits, think of less. Okay, so the first one, let's just start with methane. And we're producing water. So methane is 1605 grams. So 1 carbon, 4 hydrogens from the periodic table, 1605. Okay. And then let me just grab the balanced equation up here. Okay, so it's going to be 2, 1, and this is going to be 1802 grams per 1 mole. Okay, so moles cancel, leaves us with grams of water. Now this is ignoring the oxygen gas. I'm going to do another calculation using the oxygen gas and ignoring the methane. Okay, that's the first one. I'm going to do the same thing, only instead of methane, we're going to use oxygen. Okay, so if we're looking at just the oxygen calculation, it's 295. Just the methane calculation, it's 12.7. So the oxygen limits the reaction. That means we're going to have leftover methane because we're not going to use all the methane. Just like bicycle here, we had leftover frames. So the next question is, well, how much methane did we use then? We didn't use it all. We used part of it. So that's another calculation. So we're going to start with the limiting given, which is oxygen. Now we want to find out how much methane is consumed. So that means we're going to be looking for grams of methane. And then methane was 1605. So this third calculation determines how much methane we're using based on the limiting reactant oxygen in this case. So it's okay, so we're going to use up 1.31 grams of the methane. The next question is how much excess methane did we have? It's another calculation. Okay, so we started with 560 grams, right? And we used 1.31. And the difference is going to be how much is in excess. So we have 4.36 grams of methane left over. Okay, so that's the limiting reactant problem. Kind of like the whole page. But all of them are the same. Every one of them, step number one is figure out which limits the reaction of the givens. That's the first two calculations here. The smaller one is the limiting reagent. The next thing we have to do is find out how much of the other we used. So we start with the limiting reagent. In this case, it's the oxygen. And what we're trying to calculate now is the amount of methane used, 1.3. We started with 567, so we subtract the 131 from the 567, giving us how much excess we have. That's a limiting reactant problem. Fun, huh? You can see a bunch of you going. Okay, so any questions about this? You can see why last time I said it's imperative that you understand simple stoichiometry to do this limiting reactant one. Imperative. If this is fuzzy to you, this makes no sense. No sense at all. And I want to emphasize also, this is an extra credit problem. So if this is fuzzy to you, you don't have to do it. but you will probably run into it in your next class. How far along did you get? Did you do this? Did you do the limiting reactant one? Okay, and you were in 2A, 3A, okay. Oh, 3A, you should have had this. Yeah, so you might have dropped, yeah. Because this would have been, should have been in 3A though. Anyway, okay. All right, are there any questions about, yeah. No, normally on a limiting reactant problem, I'll ask you how much is produced. So this would be that answer. Then I'll say, how much excess is there? That's this answer. So that was a good question. Okay, any questions? Yeah. Exactly. So the first two are how much is produced. Then you look at smaller one and ignore this one, the larger one. But what you have to do now is to figure out how much of that you used, because you didn't use it all. And that's what this does. We only use 1.31 of it, of the 5 something. And that's what this is. So we started with that. We use this much. This is left over. Does that follow? Okay, now I have a whole bunch of practice on Canvas. If you go to Canvas files, let me just show you where all that is. And again, I want to, the reason why I moved that dry lab over to the special worksheet is because this is a really weak area for 1A students, 3A students, and 2A students. Very weak. So I want to make sure you guys are solid on this. Really solid. This is probably the pinnacle of this class in terms of knowledge to know going forward, along with naming these two. Okay. And I've seen it with students that came from Davis, came from Sac State, came from University of North Dakota. All of them flunked my 1A class over the summer. Now, summer classes are always difficult because you have half the amount of time, but still, and the reason why they did poorly is because their setups were awful. Because I can give partial credit if I can understand your logic, but I gave them very little credit because it was like gibberish. And they got the answer wrong. So if they got the answer right, I kind of cringe on giving them credit for it because their setup was so lousy. But if they get it wrong and I can't follow the logic, I can't give you anything. And if you do it like this in your next class at this school or Sac City, I can guarantee you, you will be in good shape. Every instructor will understand this. This is also the way your book does it. Exactly the same thing. And if you go online for some tutorials like the organic chemistry tutor or Tyler DeWitt or the, heaven forbid, the Khan Academy, lots of coffee. This is the way they do it as well. So this is a very universal process. Well labeled too, unit cancellation. All right, so let me show you where all those worksheets are with answers. Not only with answers, but with setups. Let's go into Files, Unit 4, and these are the worksheets. Down towards the bottom, there are limiting reagent problems to practice. When it says stoichiometry mass, that means it's going from grams to grams. And again, I want to stress these all have, let's see, they're also single replacement and double replacement practice as well. And this is why I don't use Mastering Chemistry. Mastering Chemistry will cost you like 90 bucks. All my worksheets are free. Who in the world has the least amount of money? Students. So I like to, of course, Canvas has got to cooperate.
There's, this is for the double balancing equations,
The double,
double displacement, yeah. No,
I don't know if there's, the only problem with my worksheets are they're more technical than what we studied in class.
okay,
So, however, if you go down to the very bottom, there's textbook problems.
okay,
So look at those problems.
okay, within the book.
The only problem is they just give you the answers, not the setup. Ah, here it is. Okay, so this is not limiting reactant problems, but I just want to give you an idea of what the worksheets look like. And then I have it set, solving it for you. But I have a jillion of these. And secondly, the if we go to modules, and we go to lab related, this is the replacement dry lab stoy or the dry lab next couple weeks. I forgot whether it's this week or next. I think it's next week. Modules. It's also in files.
at the end.
Go to lab related and go to the bottom. Yeah, right.
Oh, okay. The lab date.
No, right here.
Oh,
It's at the
okay.
top on yours and the bottom on mine.
Weird,
And that's just more problems.
okay.
Oh,
Okay. You're going to be doing this guy in lieu of your lab on dry lab on gases. Because again, I just want to emphasize the trouble you're going to have in your next chemistry class. And this is it. So I want you guys to be rock solid on this. And if you do enough of them, you will be rock solid because they look all the same. Every single one has three parts. The beginning one, convert to moles, the mole ratio from the balanced equation, and then moles to whatever you're trying to calculate. Every single one. So that's the beauty of doing zillions of them. You'll see a pattern emerge. Some of you don't need a pattern. I learn like repetition. Like I was telling you earlier in the semester, I play a lot of music and I have a really hard time memorizing pieces. I have to play it like 400 or 500 times. I'm not exaggerating. And I just sometimes I get bored playing it so much, but I get it memorized. And then it doesn't last unless I keep playing it also. And the older I get, the worse it gets. Just FYI, you guys. So, all right. So, I want to do, are there any questions about how the Canvas, where the Canvas files are located or anything like that? Okay. And I want to also recommend a pencil with a big giant eraser. Don't do this in pen. Now I'm going to do another limiting reactant problem. But if you're not interested in extra credit on the next test, we're done for the day, okay? And the only reason I say that is because it's going to be extra credit. Okay, so let's. Let's burn methane again. Okay, and then let's see. Okay, so I gotta invent a problem here now. Let's see. Okay. So right away, balance the equation. Boom. So we're starting with 34.4 liters of oxygen gas at STP. In this class, it'll always be at STP. And 33.45 grams of methane are consumed. How much carbon dioxide do we make? So let's start with the oxygen gas. Okay, that gets us 2 moles of oxygen gas. We need the ratio from the balanced equation. And then we need carbon dioxide, and that's, well, that was 44.0. Okay, so that's our first calculation. Okay. So methane definitely limits the reaction. That means we have excess oxygen. And we don't know how much. You have lab today? Tomorrow? Okay, see you tomorrow. Yeah.
1604, 1645.
On yes, it's 05, you're right. And your math is right. Yeah. That's 1201. And this is 404. So 1605. Thank you. So this number is going to be slightly different. Still going to be, in fact, sig fig wise, I bet you won't make any difference at all, I bet. Yeah. After you do 3 sig figs, it's the same number. Say again.
5 down at the bottom for
That looks like a dyslexia problem, doesn't it? Oh, how many other errors can we do with this problem? Yeah. It'd be easier. Um, let's just change it up here. There. Okay, so now we know the limiting reactant. Now we need to determine, so the oxygen gas is going to be in excess. So we need to find out with another calculation here, how much of that oxygen we use. That's the third calculation. So we're going to start with our methane. Okay, so we're going to have 1 methane and 2 oxygen. Okay, so of the 34 grams of oxygen, we only used 14.1 grams of it. So to figure out how much excess we have, and this will always be, every limiting reactant problem we're going to be doing has all these parts. Which is the limiting reactant and how much you get. Secondly, how much excess of the other. Okay, so here's your question.
So we're converting for the O2, right? Should we go into liters instead of grams then?
Um, No, because this converted to grams.
Oh, so you go.
Now, if you left it in, I mean, you could, if you'd have converted to liters of carbon dioxide, the problem is you couldn't compare the liters in grams. So you wouldn't know which, I mean, you could sort of tell if it was grossly different, but it's better to be, apples to apple. Does that make sense?
Yeah.
Okay, so, all right, so the last calculation, we start with, now see, here's a problem finding the excess. We're starting with 34.5 liters, and we're going to be using 14.1 grams. So no, that was just how much, if we ignored this, that's how much carbon dioxide we'd make. But the problem is we're dealing in liters here, not grams. So what do we have to do? Like life, convert. So instead of trying to subtract grams from liters, we're going to convert now. So we need to have this converted to grams. So now we have the liters converted to grams. Now this is about as hard a problem you have in this class. In fact, yeah, I'd say it's the hardest problem you're gonna have in this class. And it's extra credit. All right. How are you guys? Reasonable? Yeah. No. Partial. I always do that with extra credit. In fact, let me kind of tell you something I shouldn't tell you. Normally, if you put something down that's time to do the numbers, I usually give you like a point or two, just because you attempted it. But I didn't say that. Yes. So, I mean, a lot of times you can, when you start, it's like writer's block. Sometimes you just start writing something BSy. All of a sudden, it's just because then you get in the mode of writing, subject, verb, direct object, kind of stuff, and it kind of gets you in the mood and all, and you just erase all that and then go on with the same with this. Just kind of start, and that's why you big eraser. All right, that's what I wanted to cover today. And the lab's a pretty reasonable lab. It's a nice wet lab, and yeah, it's stoichiometry. I always forget the numbers. Yeah.